Hi, thanks for joining me. Today I'm going to be going over week 4, problem 3 of the Invariants Michaelmas term puzzle competition. As always, I'll leave a link in the description below with details of the competition if you want to get stuck in. Anyway, this is the problem I'm going to be tackling today. Vicky wants to write the numbers 1 to 100, so the positive integers between 1 and 100, inclusive, in a circle so that the following property holds. If we go around the circle, summing up the 100 distances between every number and the following one, you get 198. We want to know how many such configurations are there. So how many such ways are there of writing these 100 positive integers in a circle with this property here? Okay, so I've written down sort of a small circle with just 4 numbers here. So think of this as, say, a circle with 4 numbers written down. And this is just to explain this property here. By distance, we just mean the magnitude between the two numbers. So the sum of the distances going around this circle here would be the magnitude of 3 minus 7 plus the magnitude of 7 minus 2 plus the magnitude of 2 minus 4 plus the magnitude of 4 minus 3. Okay, so that's the distances between each number and the consecutive one, and we're adding them up. So here we've got 4 different distances we're summing up, and then this equals whatever it equals. So 3 minus 7 is minus 4, but the magnitude of that is 4. 7 minus 2 is 9, so 4 plus 9 plus 2 plus 1. So that's 13 plus 2 plus 1 is 16. I think that's right. I hope I haven't embarrassed myself and made a basic arithmetic error, but that's just to explain this property here. But of course we've got 100 numbers, and we want to know how many different ways are there of writing the numbers around the circle with this property here. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to get stuck into a solution. Okay, so the way we're going to solve this problem is by looking, or assuming we have a valid configuration, and then looking at some properties about that valid configuration. Okay, so I've written up, so suppose we have a valid configuration of the 100 integers around a circle. Well, firstly, let's sort of rotate this circle so 1 is at the top. Okay, and then on this circle somewhere will be the number 100. It could be right next to 1, it could be here somewhere, it could be here. I've just written it here generically. Okay, and I've written out the other 98 numbers generically as well, as A1, A2, all the way up to AT. So there are T numbers between 1 and 100. This way, T could be 0, there could be no numbers between 1 and 100, they could be next to each other. But this is just, again, the generic case. And then we've got the remaining 98 minus T numbers there. Okay, now let's look at some properties. So firstly, let's sum up the distances going around like here. So the distance between A1 and 1 plus the distance between A2 and A1, and so on. So let's start from this side here. Well, so that's going to be equal to 100 minus AT plus AT minus AT minus 1 plus, and so on, all around to the distances here. So A2 minus A1 plus A1 minus 1. Okay, now sort of by the triangle inequality, this thing here is going to be greater than or equal to 100 minus AT plus AT minus AT minus 1 plus ... all the way up to plus A2 minus A1 plus A1 minus 1. Okay, so how have I gone from that line to that line? It's perhaps easier to go from this line here to this line here, just using the triangle inequality a bunch of times. So cutting off this thing here, so 100 minus AT to give us that term, then AT minus AT minus 1 to give us that term, and so on. So this thing here is bigger than or equal to this thing here, but what's quite nice about this thing here is the middle terms will cancel, so you've got minus AT plus AT, minus AT minus 1, and then there's a plus AT minus 1 there, and so on. So all we're left with is the 100 and the 1, so that's just the distance between 100 and a 1, which we know is 99. Okay, so that tells us that when we sum up the distances in this arc here between 1 and 100, we get at least 99. And the same also holds for this arc here, using a very similar argument. So the sum of the distances along this guy here is at least 99. Okay, so that means that the total sum of the distances, so A1, the distance between A1 and 1, the distance between A2 and A1, all the way around up to the distance between A98 and 1, is going to be at least 99 plus 99, which is 198. But remember, we know that the sum of the distances between consecutive numbers is exactly 198. Okay, so that means that the sum of the distances on this guy here must be exactly 99, and the sum of the distances along this guy here must also be exactly 99. Well, when does that occur? Well, if we look back at this thing here, so we need this thing here to equal exactly 99, so not just greater than or equal to, we require equality. Well, notice going from this line to this line, the way we sort of got this thing here equals 99, we're sort of having the minus 80 plus 80, minus 80 minus 1, and so on. So you can convince yourself that going from this line to this line, to have equality, we must essentially be able to get rid of all the modulus signs. Okay, because if we get rid of all the modulus signs here, we get this same pattern of minus 80 plus 80, minus 80 minus 1 plus 80 minus 1, and so on. Well, when can we get rid of the modulus signs? Let me just draw them back on. Well, we can get rid of the modulus signs precisely when 100 is bigger than 80, when 80 is bigger than 80 minus 1, A2 is bigger than A1, and A1 is bigger than 1. In other words, 100 is bigger than 80, which is bigger than 80 minus 1, which is bigger than, and so on, which is bigger than 80, which is bigger than A1, which is bigger than 1. Okay, so equality holds if and only if the numbers here are in increasing order, and similarly, sum of the consecutive distances here is equal to 99 if and only if 100 is bigger than 80 plus 1, which is bigger than 80 plus 2, and all the way up to A97, which is bigger than A98, which is bigger than 1. Okay, so the numbers sort of going around this way are in increasing order, or if you want to think of it this way, in decreasing order. Okay, so now what we want to do is work out the number of ways there are of having the numbers on the right arc in increasing order, and the number of, on the left arc in decreasing order. Okay, so I claim that there are 2 to the power of 98 different configurations, and now to see that, well, we want to put numbers in this set here, so the set of t numbers here, and then we want to put the rest of the numbers in this set here, so the set of 98 minus t numbers here. Okay, well, so that means, and remember t is any number we want. It can be 0, it can be 1, it can be 2, it can be 98 if we want, so that's fine. Now each of these numbers here has to either go in this set of numbers, or it has to go in that set of numbers. Okay, so automatically there are at least 2 to the 98 different ways of doing it, because there are 2 to the 98 different ways of having numbers either in this set or in that set. So for each one, 2, so the number 2 can either be in this set or this set, so that gives you 2 options. Okay, the number 3 can either be in this set or that set, so that gives you another 2 options, and so on, all the way up to 98, which gives you another 2 options, and so of course this thing here is 2 to the 98. Oh, sorry, I meant to put 99 there. That's why I'm a little confused. So we have the remaining numbers 2 all the way up to 99. There are of course 98 different numbers there. So yeah, there's 2 to the 98 different ways of putting these numbers either in this set or in this set, but notice that once we've determined what numbers are in this set and what numbers are in those sets, there's only one configuration, precisely the one which has those numbers in increasing order on this set here, and those that are in decreasing order on that set there. Okay, so once we have the numbers that are in this set here, so A1, A2 all the way up to 80, and the numbers that are in this set here, 80 plus 1, 80 plus 2 all the way up to A98, the valid configuration is already determined, and there's only one, namely the one which along this set here is increasing, and the one along this set here is decreasing. Okay, so that means that there's exactly 2 to the 98 different ways of different configurations which we can use. Now I guess one small thing to end on is, remember at the start we rotated the table so that 1 is at the start. So if we're allowing for rotations as well, so for example if 1 is now, I don't know, that position there, or maybe at this position here, we still have the same number of configurations for each position of 1, so that means our total number of configurations is going to be 100 times 2 to the 98. Okay, and then we're done. That solves the problem. That's the number of valid configurations. You can write the numbers around a circle with the property that when you sum up the consecutive distances, you get 198. Anyway, I hope you have enjoyed this solution video. I hope it's made sense as well. If you are new here, please do consider subscribing and checking out some of my other fun maths videos as well. But yeah, that's all for now, and I will catch you in the next one. Have a great day.